Good morning, good afternoon, and good evening to everyone. My name is Bozhidar Klouchek, and I'll be presenting our work, which was done under my supervisor, Riza Batista-Navarro, within the Department of Computer Science in the University of Manchester, titled Bulgarian Grammar Error Correction with Data Augmentation and Machine Translation Techniques. So as a bit of background, Bulgarian is a highly inflected language. Words can change their syntax depending on an array of different factors. This includes grammatical gender, person, noun, and sometimes even the emotional charge of the speaker. I have a few examples here. So the word jump in English has few inflections. So jumps, jumped, has jumped. However, in Bulgarian, the Bulgarian word for jump, skacham, here, can have more than 50 different inflections, right? So this creates a big challenge for Bulgarian NLP researchers. The language is very difficult to work with, and this feeds into my second point, which is that Bulgarian is a low resource language. Now, in all fairness, this has improved in the last couple of years. Initiatives like Bank have consistently been giving us methods and solutions to dataset curation. And other kind of open source datasets like Oscar do contain Bulgarian data. For example, Oscar contains about 40 gigabytes of textual Bulgarian data. But then the downside that comes with Bulgarian data here is that it's very general. We don't have specialized datasets for specialized downstream tasks, right? So, for example, in error correction, one would need learner data. So learner data is something we refer to as we have a learner of a particular language, let's say English, and when they supply us with text, usually that text has mistakes, right? Because they're learning the language and they don't know all the kind of grammatical constructs yet. And then if we collect those erroneous sentences, we can then correct them via annotation, maybe by language experts, and then we get pairs of erroneous and corrected sentences. This data can then be used to train error correction algorithms to then correct sentences automatically. And Bulgarian learner data, unfortunately, is extremely scarce. We have zero to no kind of error correction datasets. So this is kind of visible in our day-to-day life. So this is a news article I've pulled from Nova TV. It's a popular Bulgarian news station in Bulgaria. You can open it on the link as well. And I assume you don't know Bulgarian, so I'll help you out. There is a mistake just in the first sentence of that text snippet I have found. And this is something which can easily be fixed by the error correction algorithm, but as established, it's just not something which is available for the Bulgarian NLP research community right now. And so this is our kind of main motivation, right? It's encouraging error correction research in Bulgarian NLP. And we've done this using our three contributions. So our first contribution is open source datasets. We have released them for research purposes, and they are a dictionary and two error correction datasets. I'll get into them on the next slide. We have also developed an error correction solution for error correction in Bulgarian. And then we have set an evaluation baseline in order for researchers to compare maybe their solutions to ours in order to encourage research in the field. So I'll start with the open source datasets now. So our first dataset is a machine-friendly dictionary. And even though dictionaries are kind of maybe basic or a standard datasets, which are kind of expected in languages already, online accessible dictionaries in Bulgarian are very much lacking. Arguably, the most famous one, supplied by the Institute for Bulgarian Language, does contain several downsides. So first off, it does not map word inflections. As we've established, Bulgarian is a very highly inflected language, and this is very necessary for the language. And this means that this dictionary isn't able to recognize if a word inflection is correct or not. It doesn't contain newer words. So words which might have come into the language because of technological advancements like the word megabyte or the word processor. Those are words missing in those dictionaries. And then finally, the whole word collection is unavailable. So typically, error correction systems have hybrid approaches. They might have a local data store of words. They would quickly check against their source. And this dictionary doesn't provide the whole word collection. So creating such dictionary-based approaches is impossible. So our solution to this is just a combination of multiple dictionary collections which already exist. So in the middle there, we see Suvoret, the one with the multiple colors. On the left is the Rechko collection, and on the right is the one I've already established by the Institute of Bulgarian Language. So our solution is for this particular problem is first collect all the word collections and then extract the words from them. Now is a good time to mention that words in Bulgarian, when they get inflected, usually we append articles or particles to them. And so we'll see, for example, the first word here is just a single token word, but the second and third are multi-tokens. So to simplify the task, we perform just basic white space tokenization, and we extract the most important words, the most important token, out of the multi-token one. And then we pass over the part of speech tags from the original word collections in order to remember them and contain them in the dataset. So this would ideally allow someone to build a dictionary-based spelling error correction system. We have also provided the spell error correction dataset. So as established, learner data is very scarce. So instead of looking for natural learner data, we instead induce spelling errors using phonetic phenomena. So just for an example, in English, there is a phenomenon called assimilation. So given a source token here, which is cupboard, the P sound almost always doesn't get sounded in the actual pronunciation of the word cupboard, which leads learners of English to forget it and just write cupboard without the P. So that's an example of how phonetic phenomena kind of motivates spelling errors. And it's very similar in Bulgarian. We have the word shkaf, which can be written with a F instead of a V, again, because of differences in pronunciation. And this is how we kind of create a spelling error dataset. It's more on the token level, and we use other phonetic phenomena we have explicitly described in our paper. In terms of the grammar error dataset, which is arguably a bit more interesting, it focuses on the sentence level as opposed to the token level. So instead of trying to change the syntax of tokens, it attempts to recognize grammatical structures and switch out tokens by their part of speech tags. Now, what does that mean? If, for example, you have a source of a sequence of tokens, they would first be tagged. So each token will have its own tag. And then we'd identify a token of interest. So for example, the second here might be a token of interest. We'd switch out the tag with a different one and thus changing the token in order to make a mistake. So for example, here we have the man sits on a chair. If we choose sits as our token of interest, we can change it to the man sits on the chair. So this is how we create the grammatical error. So let's actually delve into this a bit deeper. So we have a source sentence here. So this is a source of a sequence of tokens in Bulgarian. It's a correct sentence, which first would be applied part of speech tagging. So we have the 4 tokens and the 4 tags. It's pretty self-explanatory. So the next step would be identifying a tag pair. Now we have specific mappings we've described explicitly in our paper. But let's say we take the first one here, which is from the yellow tag to the orange tag, right? And we immediately notice in the source sentence, we already have the yellow one. So our motivation here would be to switch it out with the orange to induce a grammatical mistake. So we've identified it, and now we want to pull our new token. So we pass the tag of interest, the new one, and the old token to pull the new one, which is it's a correct word in Bulgarian, but incorrect in the given context. So we pull the new token, and it's as easy as just switching it out in order to create a grammatical mistake. And from source sentence, we get a target erroneous sentence. And this is how we're able to generate a large dataset of grammatical mistakes. And we use that specific dataset to fine-tune our own solution. So our proposed solution for this problem is a fine-tuned MT5 for grammar error correction. It's a sequence-to-sequence model. So it's built from T5. The M stands for multilingual. So it also is able to communicate in Bulgarian. The way it gets fine-tuned is very similar to the way neural machine translation works. It's just that we interpret our source language as incorrect Bulgarian and our target language as correct Bulgarian. So we're able to correct sentences automatically in that way. So we do this, we fine-tune our MT5 for grammar error correction. We perform a grid space search in order to kind of achieve the optimal model. We look over weight decay, learning rate, and training batch size. And we train those 18 combinations for 16 epochs, and we repeat the whole process 3 times. This is done to ensure that the random neural network weight initialization is taken care of. And so after we do this, we then want to evaluate. We've chosen 2 models to compare against. So those are contemporary models, GPT 3.5 Turbo and Bulgarian GPT. Now, this is a very odd naming convention. Bulgarian GPT is not the GPT model. It's actually a fine-tuned version of Mistral 7B. So in order that no one gets confused. So we use those 2 models to evaluate against our solution. And here we have the numerical results. So we've chosen precision, recall, and F0.5 score as our metrics. F0.5 as opposed to F1 because precision is more important in grammar error correction tasks, thanks to literature. And you immediately notice recall is pretty much same across the board. That's because most models are able to correct the mistakes, right? But where our model really shines is precision. Our model is able to avoid overcorrection by specifically correcting only errors which are actually real errors as opposed to just correct tokens. So that's our evaluation. And then just a few more notes. We've performed sequence-to-sequence modeling to solve this task, but we've evaluated it against GPT and Bulgarian GPT, which are both decoder-only models. Now, usually you would compare it against sequence-to-sequence models. However, there is a very large scarcity of sequence-to-sequence Bulgarian large language models, which unfortunately leads us to kind of choose what's available in order to evaluate. And we've also performed a qualitative evaluation, meaning we made a survey with 67 native Bulgarian speakers in order to get a better understanding of the kind of subjective aspects of our model. And our model was chosen as the most readable and the most comprehensive. And finally, I'll just reiterate what our contributions. So we released 3 datasets, a dictionary with 1.15 million rows, spelling and grammar error correction datasets with corresponding roles as well. We've developed a fine-tuned MT5 solution for Bulgarian grammar error correction. And finally, we have evaluated and proposed a solution which achieves a state-of-the-art task in grammar error correction. If anyone is curious, all of the datasets and the model are available on Hugging Face, and they're available for research purposes. And we hope this motivates more error correction research in Bulgarian. That's everything. If anyone wants to ask anything, you're welcome to.